Hi, so I'm going to be talking a little bit about the computational complexity of the ground state energy density problem, which is work between myself and Toby Cubitt. So as many of you may already be aware, determining the properties of a general physical system is actually quite difficult in general. Unfortunately, we can't usually write nice closed form analytic expressions for the properties of the physical system, and so we have to resort to computational methods. And so what we want to do is we want to use computational methods to understand the Hamiltonian, the thing that describes a physical system as fully as possible. And Hamiltonian complexity is a subset of, or a subfield of quantum information and computer science, which studies which Hamiltonians and which of their properties can or cannot easily be determined. And we can classify families of Hamiltonians based on the complexity, of their properties, and often their complexity tells us something about the physics of the system. So if I give you a physical system, one of the first questions you might ask about it is, what is its lowest energy state? And so a natural complexity question to ask is, how hard is it in general to determine this lowest energy state? So this lowest energy state, sometimes called the ground state. And this is computationally characterized by what's called the local Hamiltonian problem. So in the local Hamiltonian problem, I input a description of my Hamiltonian H, acting on n qubits, and a pair alpha and beta separated by 1 over a polynomial. I promise you that the ground state energy, or the lowest energy state of our Hamiltonian, is not in the interval alpha beta. And if I output yes, or if the ground state is less than alpha, then we output yes, and otherwise and if it's greater than beta, we output no. And the reason this is kind of computationally equivalent to approximating the ground state energy is because you can imagine choosing beta alpha and beta, getting an answer, choosing another alpha and beta, getting another answer, and doing a kind of binary search procedure to narrow down the interval in which the ground state energy lies. And a while ago now, the kit I have showed that this problem is QMA complete, and so it's believed to be intractable even for a quantum computer. And we can classify families of Hamiltonians based on their hardness of a local Hamiltonian. However, if you go back and read Kittiev's original proof, it only proves QMA hardness for Hamiltonians which are 5 local, non-geometrically local, non-translationally invariant, and have no underlying lattice structure, for example. And these aren't particularly physically natural problems. And so you might ask, if I restrict Hamiltonians, or I restrict to physical systems which look like those that appear in nature, does this problem suddenly become computationally easy? And the answer appears to be no. Some very smart people came along and they showed that even if you just have qubits on a lattice, so a spin-2 system on a lattice, or you have a translationally invariant nearest neighbor system on a one-dimensional chain or one-dimensional lattice, then this problem remains computationally intractable. And you can study problems beyond just determining the lowest energy of a physical state, beyond the local Hamiltonian problem. So people have studied, for example, determining the expectation of local observables. So measurements you can do on a physical state, determining the density of states, looking at the energy landscape of Hamiltonian, lots of other very physically well-motivated problems. However, all of these problems that we've looked at, or I've described previously, are phrased in a particular way. So all these previous results are concerned with finding some property of a physical system to a fixed precision depending on the Hamiltonian. And the Hamiltonian and the precision varies with each problem instance. So you can think of this as, this problem naturally characterizes the problem where I have, let's say, a set or a family of molecules or something, and I want to find out the lowest energy state of each of these molecules to a fixed precision. And while that's certainly very physically motivated, that's not necessarily the quantity or the problem that we're always interested in. In particular, if I'm a physicist, one of the problems that I might be interested in is where I have a fixed physical system, a fixed Hamiltonian, and I look at the case where the number of particles goes to infinity. So this is called the thermodynamic limit. And the reason we consider the thermodynamic limit is because it really describes the bulk properties of a material, where there are no size-dependent effects. And also there are a lot of physical phenomena which are only really defined in the thermodynamic limit. They're only really defined where I have an infinite number of particles. Examples include phase transitions. And it's often the case where that I have a pretty good approximation to my problem already. What I'm actually interested in doing is looking at the problem of increasing the precision to which I know some physical quantity. And so some physical systems that we might study this way include, for example, the Fermi-Hubbard model, which is given at the top here, which is believed to be a model of high temperature superconductivity. And also lattice quantum chromodynamics, which is a description of the strong nuclear force and quark interactions. So both of these systems are kind of poorly understood, and we want to be able to study their properties in the thermodynamic limit. But from a complexity perspective, the local Hamiltonian problem and other similar problems don't really describe the problem that we're computationally interested in. So one thing I should note is there actually are a bunch of results about Hamiltonians in the thermodynamic limit. However, all of these deal with families of Hamiltonians rather than fixed Hamiltonians. So, for example, it's been shown that determining the spectral gap of a one-parameter family of Hamiltonians in 2D and in 1D is undecidable. Determining phase transitions for a one-parameter family of Hamiltonians is uncomputable. Determining the energy density of a slightly weirdly parameterized family of Hamiltonians is QMA-X complete. So these results aren't really important for our purposes, but just to say that in all of these cases, the local terms vary with the instance. So you're studying different instances correspond to different physical systems. So that's not quite what we're studying. And what we're trying to study here is a fixed physical system. But if you're a complexity theorist, you might turn around to me and you say, does it even make sense to study the complexity of a single property of a fixed Hamiltonian in the thermodynamic limit? Surely this is a fixed quantity of a fixed physical system, a fixed Hamiltonian, and so it's just a single number. You can't really study the complexity of a single number. And I'm hoping to convince you that this is not the case. And the quantity that I'm going to argue we can study in this way is called the ground state energy density. So the ground state energy density is really is defined for a two-dimensional Hamiltonian lattice as just the ground state energy of your lattice divided by the number of particles in your lattice. So it's the energy per part, or the minimum energy per particle in your lattice. And what we're going to do is we're going to study the problem of increasing the precision to which you know the ground state energy density. So how hard is it to increase our precision from 4 bits of precision to 5 bits of precision to 6 bits of precision, etc., etc., etc. So in order to study this as a computational problem, we need to define it as a computational problem. And so there are two ways of doing so. First way is as a promise problem. So in this, I have a set of problem parameters which describe my Hamiltonian, but this is going to be fixed for all instances. And our input is going to be a pair of numbers, alpha and beta, in binary, which are not equal to each other. And I promise you that the ground state energy density, E of rho, is not in the interval alpha beta. And I output yes if the ground state energy density is less than alpha, and no if it's greater than beta. Alternative formulation is the function problem version, in which the local Hamiltonian terms are fixed. These local interaction terms describing the physics of the system are fixed. And I ask for an estimate of the ground state energy density to some precision epsilon. And I get out an estimate, which is within precision epsilon. So if you're, normally when we're considering promise problems or something or similar, we have a conditional on alpha and beta, which is they scale as the difference between the scales as 1 over a polynomial, 1 over an exponential, or whatever you're studying. But in this case, because there's no notion of a system size or an amount of information associated with the system, alpha and beta themselves define the input length. So in fact, beta minus alpha defines the number of bits of precision that we're working to. So it essentially defines the precision in the same way that the input to the function problem is the precision. And I really want to emphasize this, this point a little bit more. When we previously considered the local Hamiltonian problem, or its translation invariant Hamiltonian, local Hamiltonian, when we considered the local Hamiltonian problem or its translation invariant version, our input consists of not just only alpha and beta, but a description of the Hamiltonian and its system size. From the translation invariant case, just the system size. And so different instances of the problem correspond to different physical systems. Whereas here, different instances of the ground state energy density problem are going to be defined only by the precision. And so we're really studying changing the precision for a fixed physical system. So these are qualitatively different problems. And so with that in mind, I'm going to jump straight into the results. So we showed that for fixed translation invariant nearest neighbor classical Hamiltonian, that the ground state energy density satisfies this following set of relations. So the ground state energy density promise problem is contained in next. And then it's X with a GZ oracle contains P to the next, and X with a and is contained by X to the next. And the intuition that you should think, or the way you should think of this is that increasing the precision to which you know the ground state energy density by constant number of bits is at least as hard as next. And in case it's maybe not totally obvious, here next, or NX, is NP, but with an exponential witness length and runtime. And next, or NX, is NP, but with a doubly exponential witness length and runtime. And so if it's not maybe totally intuitively clear what our results are saying, I think hopefully it'll become a little bit clearer if I give you a kind of overview of what the proof looks like, which I'll try and do. So what we want to do is we want to find a way to encode a countable infinity of problem instances into the ground state energy density. So we're going to try and construct a physical system, a Hamiltonian, which has a ground state energy density of the following form. It's 0.00 I1, 0.00 I2, 0.00 I3, where here I1, I2, I3, etc. are going to be solutions to instances of some Neeks complete language. And so we see that increasing the precision of the ground state, to which we know the ground state energy density, corresponds to giving us the answers of successive Neeks instances. And so that's all very nice and easy to say, but what we need to do now is to construct a Hamiltonian physical system which has this property. And the way we're going to do this is we're going to start by encoding, we're going to start by looking at not a Hamiltonian or physical system, but a set of tiles. So we're going to start by encoding the evolution of a Turing machine into a set of tiles on a two-dimensional grid with markings. And these tiling markings determine whether one tile can be placed next to another. And rows of tiles are going to form a Turing machine tape at a given time step. And each tile is going to form a cell on the Turing machine tape. And tiling rules are going to enforce the correct evolution of the Turing machine. So this is quite a well-known construction. I think it's from Berger back in the 60s. And it's best illustrated just by a diagram. So imagine I have a 5x5 grid. And at the bottom, I place so five tiles, which represent my initial Turing machine tape. And the red marking here with an A next to it is just representing the Turing machine head in state A. And then the tiling rules, as I tile the grid, enforce the way in which the tiling tiling happens. And they, in this case, are going to enforce the evolution of this Turing machine. So successive rows here are going to correspond to the Turing machine tape at given time steps. And now what we're going to do is we're going to map each tile type from this grid to a spin state in a Hamiltonian, also on the same size grid. And what we're going to do is we're going to introduce energy penalties which penalize states when the corresponding tiling rules are not obeyed. So the ground state, or the lowest energy state of the Hamiltonian on the grid, is going to correspond to the correct tiling, which in turn is going to correspond to the evolution of a Turing machine. But having this by itself is not going to be enough to encode in countable infinity of instances in the ground state energy density. So we're going to introduce another set of tiles called the Robinson tiles. So these are a set of 5 tiles with these markings. Don't worry about the markings. They're not particularly important for our purposes. They have tiling rules that arrow tails mean arrowheads. But what's important is that they generate a quasi-periodic pattern of squares. So if I ignore some of the markings, you can see that, or it turns out that they generate a pattern on a small grid that looks something like this. So you have a set of squares. And then on a slightly larger grid, they generate a pattern like this. And as you tile a larger and larger grid, you see that they tile a pattern that looks something like this. So it's a little bit trippy. I'll give you a moment to kind of take that in. But the basic idea is that they generate a series of expanding nested squares which go up, or their size goes up as powers of 4 to the power of n. And we see that larger squares appear with lower densities. Okay, so now we're going to combine our Turing machine or tiled Turing machine construction with these Robinson squares. And in particular, what we're going to do is within each Robinson square, we're going to encode a Turing machine. And in particular, in squares of size 4 to the power of n, we're going to choose the Turing machine to run the nth instance of a next complete problem. And then we can assign an additional term to our Hamiltonian, which gives an energy penalty to any instance which outputs no. So that squares that contain rejecting computations receive energy 1, and otherwise they receive energy 0. So if lambda to the 4 to the n is the energy of the a square of size 4 to the n, then we see its energy is either 1 or 0, depending on whether the nth instance of this next complete language is yes or no. And it turns out if you go away and compute the ground state energy density, it looks something like this. So larger squares appear with lower density, and so contribute less to the ground state energy density. And we get out a ground state energy density, which looks exactly like what we want. So I've glossed over a very important point here, which I need to prove that this state, or the state that we claim is the ground state energy, or the ground state, is actually the ground state. This is non-trivial, because you can imagine that introducing a tiling defect, which allows a break in the tiling rules, may allow us to destroy encoded Turing machines. So you can imagine, let's say, if I have initially a perfect Turing machine grid, if I introduce a tiling defect in the center row, I could flip one of the bits in the Turing machine tape. And if this corresponds to a no instance of my language, we know this Turing machine will pick up some energy. So it could be the case that introducing a tiling defect will flip the no instance to a yes instance and thereby lower the energy. But it's worse than that, because you can also destroy the Robinson tiling in which the Turing machines are nested. In particular, if I have n defects, we can ensure that they receive an energy penalty proportional to n. But it could be the case that n defects destroy something or more than order n Robinson tiles or Turing machines in the tiling pattern. And so this would mean it's energetically favorable to have tiling defects, since they can destroy Turing machines, and these Turing machines have a positive energy contribution. And in particular, it's very possible this might happen for this construction. The aperiodic pattern, these kind of large expanding squares, mean that the effects of defects can propagate arbitrarily long distances. So in order to bound this, we use a slightly weird construction. So suppose that there are a set of defects in your tiling grid. What we do is we take the Delaunay triangulation with the defects as vertices. So this is just a triangulation of the defects. And one can prove that within a triangle in the Delaunay triangulation, if a Robertson square of size 4 to the n is not within distance 4 to the power of n of an edge, then the kind of associated tiling has to be intact in some sense. It can't be destroyed by the defects. So I've drawn a very poor diagram here, which is basically to say if I have a triangle, or if I have lines in the Delaunay triangulation, the tiling far away or some distance away from the Delaunay edges has to be intact, and as well as the associated Turing machines. And this essentially limits the area that the defects can damage. And you can show that the number of Turing machines destroyed is proportional to the number of edges in the Delaunay graph. And in particular, the number of edges in the Delaunay graph is bounded by 3 to the n, because it's a planar graph. This shows that the number of destroyed Turing machines must be bounded by something that goes as order n, so order of the number of defects. And by penalizing the defects energetically sufficiently largely, you can show that defects are energetically unfavorable to appear in your lattice. So this shows that the design state is in fact, or this state, which is squares nested within squares nested within squares plus the Turing machines, is in fact the ground state. So a very natural question. So this proves that that our construction gives us the ground state energy density that we want, and it proves hardness of the classical case. But a very natural question is to ask, what happens about if we consider a quantum Hamiltonian? Well, our results change slightly, or at least the upper bound for our results change quite slightly. So for quantum Hamiltonians, we get a result that you get a different containment in the class Q to the QMA x, which is just the exponential version of the class QMA. But we can't, or so far we haven't managed to prove hardness for a quantum complexity class. So why is that? Well, it results from the definition of most quantum complexity classes as promise classes. So in particular, just using QMA as an example, you may recognize the definition of QMA to be the set of promise problems for which on an input X, there exists a polytime circuit or a poly-size circuit such that if X is a yes instance, then it accepts a witness with probability greater than 2/3. If it's a no instance, it accepts no witness with probability greater than 1/3. But this is, let's see, to open a kind of another case. What happens if I input an X which has a maximum witness acceptance probability between 1/3 and 2/3? Well, you could ask, okay, what happens if I try and encode or I try and prove hardness for a quantum complexity class like QMA, and we can try and do that. So the natural thing to do is to encode the computation of encode the QMA verified circuit in a local Hamiltonian using Kitaev's well-known circuit Hamiltonian mapping. And you can show that the energy of local Hamiltonians corresponding to valid QMA instances can be found exactly, or modulo some details. But it turns out that as soon as I input an invalid instance, it turns out that there's you can't really say anything about the energy. So this is a problem because if I try and use this Robinson square construction or something similar, and we're not able to just use valid instances. I have to enumerate over all instances, and so, or I can enumerate over all inputs. And so while the first two instances may be valid instances, eventually I'm going to hit an invalid instance, and the uncertainty or the error in my knowledge of the energy of the invalid instance will essentially drown out my ability to extract instances further down the bit string. And this essentially this uncertainty is wiping out my ability to extract later instances. And this is where our proof fails, and we don't know a way around it at the moment. So in summary, the ground state energy density problem characterizes the problem of estimating the ground state energy density for a fixed Hamiltonian on an infinite lattice. And as far as we know, it's the first complexity result for a fixed physical system. And as far as we know, the first complexity result, or the first non-trivial complexity result for a fixed number. And hardness for quantum problems is unclear. So there are a bunch of open questions, such as what the tight complexity bounds, how do we avoid invalid queries for promise classes, are there alternative ways of formalizing these precision-based problems, are there other natural problems of this kind, and are there more natural complexity theoretic formulations for promise versions. And finally, I should note that there is another talk at STOC this year by Dorit Aronov and Sandy Irani on a very similar topic, and I thoroughly recommend that you check out their talk, as it complements ours very nicely. So thank you very much for listening.